Welcome to the Joy of Math. I am Dr. Murray Siegel from Sam Houston State University. And hopefully over the next 24 lectures, we will investigate and determine the importance of mathematics and many things possibly you don't know about mathematics. Hopefully I will be successful in that. This first lecture, which is entitled An Introduction and the Counting Numbers, I plan to do three things. The first is to sort of introduce the course. Wouldn't that be nice? The second is to introduce myself, since many of you have no idea who I am. And the third is to begin looking at mathematics by looking at the counting numbers. So let's start with what this course is about. I look at this course as a tapestry, weaving various parts of mathematics together, looking at the history of the development of mathematics, looking how human beings first searched for understanding of the world through numbers. And as their brains developed and as the world got more complex to them, how the mathematics followed until we have today with computers and flying in space, etc. We're going to look at connections between mathematics and the real world. And sometimes we fail to realize when we're using mathematics or mathematics is used for us in our day-to-day lives. We're going to look at patterns. A lot of this course will involve patterns because I am a big believer that patterns are important, and mathematics is all about patterns. And of course, pattern recognition is a key tool in problem solving. We use mathematics all the time, and this series will analyze various applications. Not necessarily every application will be germane to your life, but hopefully I will touch on things that you'll say, yes, I do that, and perhaps not even realizing the amount of mathematics inherent in that application. Mathematics in this series is divided into 7 primary areas. If you were a mathematician, you'd say there were 7 subsets. The first are numbers, and we'll look at the basis of mathematics. Fundamental counting numbers to abstractions of the complex set of numbers. Then we'll look at algebra. Again, this is not an algebra course. We have those other series, but we'll just look at the creation of algebra and how it generalizes arithmetic, plus providing a symbolic language for sciences and other applications, including business, I might add. Calculus is our third area, and this is not, again, an attempt to teach you calculus, but to look at calculus as I see it, which is a philosophy class, a philosophy of change, and of course change is very important. Our investigation of astronomy, of the heavens, and how we just do business is relying upon calculus all the time. It's a very important facet of human effort. Then we come to a one lecture set called fractals. Fractals is a relatively new area of mathematics, which is being used to develop models to attempt to understand chaotic situations. And fractal geometry also, as we'll see, provides great beauty. It's actually magnificent. I am swept away every time I see fractal designs, and I think you'll hopefully feel the same way. And we're just scratching the surface on fractals. The fifth area is geometry, which literally means to measure the earth. And it goes back to the tax collectors of the Egyptian pharaohs. And geometry teaches us precision and a logical approach to things. If you ask many high school mathematics teachers, they will tell you that they teach geometry because they want their students to understand logical thought processes. I'll leave that up to you to decide whether it's true, but certainly geometry has that ability. And then we'll talk about probability, as looking at outcomes of gambling situations, which is how probability actually started and eventually became a scientific tool to deal with the variation of life. And then statistics, or if you will, data analysis, or data analysis for those of you from different parts of the country, where that is really not mathematics. It's an intense user of mathematics. It really is a social science. And we'll take a brief look at collecting data, displaying and analyzing it, and look at how, for example, in some things as political polls and statistical process control in industry, how this is used and how that uses mathematics. So that's where we're going. And hopefully, when we're all through with lesson 24, you'll say, okay, I've learned a few things. But now I want to tell you who I am, because where do I stand, coming here to tell you about the beauty of mathematics and about the importance of mathematics? Well, First of all, I am a teacher of mathematics. That's who I am. I am not a mathematician as such, although I'm a member of the mathematics department. My primary job has always been, since I entered the profession, teaching. And I have also had various jobs. Some people would say that I can't hold a job. Other people believe that I am in the witness protection program, keep moving around from job to job in various geographical locations. But I've used mathematics, and I've taught mathematics in the last 25 years in public schools. I've taught it to young people and junior high school age students and high school age students. I've also taught as an adjunct faculty member in various 2- and 4-year colleges and universities. And of course now I am at a 4-year university where my primary responsibility is actually teaching mathematics to future teachers, something I take as a very big responsibility. I have also taught mathematics to adults, not only via tape through the teaching company, but also in workshops and special adult classes, because there are many adults, and some of you may be some of these, who believe that they cannot learn mathematics. And hopefully one of the purposes of this course will to make you feel more comfortable with mathematics. I have also used mathematics as an engineering student, and for a while, coming out of college, I had a job as an assistant to a plant engineer in a commercial bakery, and used mathematics on a day-to-day basis. I served as a flying officer in the United States Air Force and used mathematics both in navigation and in electronic warfare. Prior to becoming an educator, or a teacher, as I like to say, I was in the business world. I worked on Wall Street, I worked in manufacturing, and basically mathematics was part of my job no matter what I was doing. So I really came to appreciate the importance and the application of mathematics. As a student of mathematics, and obviously I've taken many mathematics courses, I have then used my knowledge of mathematics as both a consumer and as an investor, because occasionally I make enough money to have money left over to invest. And in reality, mathematics is quite important in looking at investment possibilities. I honestly believe that mathematics is a subject not only for a select elite. If you lack confidence in mathematics, I really truly hope that this course, this series of lectures, will convince you that the subject can be understood and appreciated by all people, but most especially by you. Let us start with our investigation of the joy of mathematics. Let us look at the tapestry in the creation of this vital subject. The first kind of numbers that we deal with are the counting numbers. Sometimes they're called the natural numbers because they occur naturally. In fact, as I will try to show, they are the only numbers that you can show me. And these are the numbers created by the earliest human beings. They used their fingers to count. And eventually, to communicate those counts, they either showed their fingers or made grunts or sounds associated with each number of fingers. Eventually, to communicate these numbers, they made scratches on a rock or possibly scratches on a wall to record events. Eventually, these words, these sounds became numbers. And for example, what would they do? Well, they might, in fact, in a clan, be counting the number of clan members to see if anybody had left or been kidnapped. The number of animals that have been killed for food. If they knew how many animals they needed to keep the clan in food for a week or whatever it was, they would have to know how many animals they had killed. The number of bowls, the number of knives, even the number of moons, passage of the moons, since the last time something exciting had happened. Basically, they recognized that they could count these things, and the human mind created symbols and sounds for these numbers. And this was the very beginning. And eventually, we come to ancient Egypt. And in ancient Egypt, it was really the first attempt of civilization to really mathematize the world. And the Egyptians developed hieroglyphics to represent language and also to represent numerical quantities. This first happened in 3400 BC. And that is always amazing to me. You think about that. That is approximately, give or take a couple hundred years, 5,500 years ago. And people were already coming up with complex symbols to represent numbers. The Egyptians used a rod to symbolize 1, an arch sometimes interpreted as the heel of a hand to represent 10, A scroll or coil represented 100. A lotus flower was used to stand for 1,000. Eventually, the Egyptians created symbols for 10,000, 100,000, and 1 million. The hieroglyphic for 1 million was supposed to represent an astonished man. I've always assumed it was a gentleman receiving his tax bill from the Pharaoh. After the Egyptian civilization, and another major contribution happened some 1,000 years later, in 600 BC, or thereabouts, the Greek civilization began to use letters of their alphabet as numbers. Again, while the Egyptians had symbols that were symbolic, in other words, it was not letters, symbols stood for words, the Greeks had a language with letters, and the letters combined to form words, and the words sentences, as we do today. Those same letters were used to represent numbers. The first 10 letters were the numerals 1 through 10. The 11th letter in the Greek alphabet, kappa, represented 20. The next 7 letters represented 30, 40, 50, 60, 70, 80, and 90. Rho was 100, sigma 200, tau was 300, etc. At the same time, the Hebrews and the Phoenicians, which both had Semitic alphabets, were also using letters to represent numbers in a way similar to the Greeks. And basically, this led to some interesting things we'll see later on. The Romans also used letters of their alphabet, but instead of using all the letters, they only used certain letters, and then developed a way of writing numbers that is still, in fact, used today on buildings and clocks and such. Little is understood about the earliest development of Roman numerals. But in 500 BC, the Romans had overcome the Etruscans, and early Roman monuments, have inscriptions using Roman numerals. So we know that, about 500 BC, Roman numerals were in use. And most of us, if not all of us, are familiar with Roman numerals. The I representing 1, which really is a single finger. V representing 5, V being a hand. X representing 10 or 2 hands. The original Roman symbol for 50 was an arrow facing downward, which eventually became an L, which is, of course, still used today for 50. C was the Latin word, from the Latin word centum, meaning 100. M for the Latin word mille, representing 1,000. The D, which was used and is still used for 500, was actually 1/2 of a symbol that was used for 1,000 before M became the common 1,000 symbol. The Romans used addition and multiplication to write their numbers. Unlike today, originally 4 was I. Subtraction was not used until much later on. For example, writing the number 862, you'd have D followed by CCC, LXII. The D is 500, the 3 C's 300, total 800, LX 60, and II 2, 862. Until the Middle Ages, VM did not mean 5 less than 1,000. In fact, it still wouldn't do that. V is not used as a subtractive element in Roman numbers even today. But when you had a letter that was of smaller value preceding a letter of greater value, that is, V was less than M, it meant to multiply. So VM was 5,000, 5 times 1,000. Once the printing press with movable type was invented, the use of subtraction became common in writing Roman numerals, again, trying to become efficient in the use of symbols. So that, there was hundreds and hundreds of years of Roman numerals without the subtractive element. A number system that was based on place value was desperately needed to make computation easier and to allow for the writing of extremely large numbers. Remember now, human enterprise was becoming much more complex. You can add and subtract with Roman numerals, but try sometimes to multiply or divide. It is not an easy task. The Hindus in India developed such a system, that is, a system of symbols with place values. Little is known about the influence of Greek, Babylonian, and the Chinese number systems on the evolution of the Hindu system. Arab armies spreading Islam, invaded India. And the Arabs recognized immediately the value of the Hindu number system and adapted the idea, brought it back to Baghdad, the center of their culture and civilization, where it became an Arab system. But they always gave credit, and even today it's called the Hindu-Arabic number system. In 825, the numerals, the forms and the concept of place value had been accepted by Arabs, but credit was always given, like I said, to the Hindus in developing the system. So 825, the Hindu-Arabic system spread across North Africa and into Spain as the Muslim armies invaded and conquered these areas. But it was not accepted in Europe because it was created by non-Christians. In the 13th century, Leonardo of Pisa, sometimes called Fibonacci, used the Hindu-Arabic system in his writings. He had traveled in the Muslim world. His father, I believe, was a merchant, and realized the importance of using this new numerical system. And he convinced the European scholars. He was so well respected that when he used the Hindu-Arabic symbols, other scholars started to do that, and the Roman numerals began to disappear, but not totally. By the 15th century, the printing press caused the use of the 10 numerals to become standardized. Again, it was very efficient. But the Hindu-Arabic system did not replace Roman numerals in many European schools until the end of the 16th century. And European bookkeepers did not uniformly use Hindu-Arabic numerals until about 1700. Shows you that some people can't realize when they have a good idea. What I'd like to talk about next is a modulo number system, because the fact is that most of us are used to using our number system and unlimited numbers. We can write one with a million zeros after it and give a name to it. The modulo systems are interesting because the modulo systems only use a limited number of numbers, not just digits. So, for example, a modulo 5 system would use 5 numbers, 0, 1, 2, 3, and 4. And a modulo number system is sometimes called a clock system, because in a clock, the clock goes around, and when you get to 12 o'clock, you start all over again. An analogy I like to use, if you go to an old minor league baseball stadium, a park, and they have the old hand-driven scoreboards, they will have one place where they show strikes, and they will have the numbers 0, 1, and 2. They will not have 3, because either you have 0 strikes, 1 strike, or 2 strikes. 3 strikes, you're out, and it's the next batter. It's the same thing here in this modulo 5 system. We have 0, 1, 2, 3, and 4, but we don't use 5, but there are 5 numbers, and it's the only numbers. There's no 6, there's no 10, there's no 23, there's no -3, just those 5. In modulo 5, or mod 5 as it's called, 4 plus 3 equals 2. Why does 4 plus 3 equal 2? Because, well, it equals 7, you say. But there is no 7. Again, we only have the digits 0, 1, 2, 3, and 4. And, of course, 7 is 2 more than 5, which, of course, is 0. So, therefore, 0 plus 2 is 2. If this is confusing, that's good. Because the idea is we get very self-satisfied with something we're familiar with. And we're all familiar with our numbers. And, therefore, sometimes we need something a little different that challenges our mind and says, wait a second, let me think about this. Let's take a look at the modulo 5 number multiplication system. 4 times 4. Well, let's see. 4 times 4, that's 16. But there is no 16. There's no two-digit numbers. There's no number beyond 4. How would you do that? Well, what is 16? 16 is 3 times 5 plus 1. So which means you'd go around the clock 3 times, and then one more would be 16, which is 1. So in the modulo 5 number system, 4 times 4 is 1. Now, the modulo 6 table, again, let's talk about that. The modulo 6 table would use 5 numbers plus 0. That is 0, 1, 2, 3, and 4, and 5. It would limit itself to those 6 numbers. There's no 6. And if we were looking at the multiplication table, we would see that 1 times a number is itself, so 1 times 3 is 3, and 3 times 1 is 3. But you'll notice that 3 times 2 is not 6, because there is no 6. Because when you've counted 3 plus 3, you're back to 0. So 3 times 2 is 0. In the modulo 5 table, you will see that each line of multiplication has all of the digits. 1, 2, 3, and 4. 1, 2, 3, 4. In the modulo 6, it does not. For example, 2 times anything. 2 times 2 is 4, but 2 times 4 is also, 2 times 2 is 4, and 2 times 5 is also 4. So we have a problem, if you want to call it a problem, a challenge mathematically, to begin to look at different multiplication tables and recognizing that in some multiplication tables, we have a situation where each line of multiplication table contains all of the digits in that number system. 5 was an example. Another example is 3. Another example is 7. Now, the modulo 6 system does not have that. Some of the lines have 1, 2, 3, 4, and 5. Other lines do not. They are limited to only some of the digits, and therefore there's repetition. The question a mathematician would ask, and this is one of the things I try to get across in this whole lecture series, is how does a mathematician think? Because many people think mathematicians simply go out and add, subtract, multiply, and divide, do algebra, calculus, geometry, or what have you. No. They think. They observe, they make hypotheses, they test the hypotheses, and come up with new situations, new rules, or new questions. So the question is, 3, 5, and 7, all those multiplication tables in the modulo systems all have each line containing each digit. 6 and 8 and 4 do not. What's the difference? And the first conjecture would be, well, maybe odd modulo systems, 3, 5, and 7, do, and 4, 6, and 8, even systems, do not. So we take a look at the modulo 9 system. And the modulo 9 system has some rows, 1 and 2 and 4, 5, 7, 8, all have all the digits. But 3 and 6 do not. So our conjecture that odd modulo systems would work and even would not does not work. And again, that's okay. It's not, you make a conjecture and you find, no, that doesn't work. And we continue on, and we'll find that 11 and 13 and 17 are odd systems that do have the rule, but 15 does not. 15 has rows that have repetitions and do not have all of the numbers. And remember, in a modulo 15 system, you would have the numbers 0 through 14. So there are 2-digit numbers there, but nothing beyond 14. Well, do you see a pattern? If you recognize that 3, 5, 7, 11, 13, and 17 are prime numbers, then you might see the answer to the question posed. That is, where do you have modulo multiplication tables with each line containing all the digits? And the answer is, if the modulus, if the number you're using as the base for your system is prime. If it's composite, that is a number that has factors other than one of itself. For example, 9 is 1 times 9, but also it's 3 times 3. This odd number will not. And of course, all even numbers except 2 are divisible by 2 and therefore are not prime. But what are the prime numbers and how were they discovered? Because prime means important. Well, back in ancient Egypt, people were trying to figure out what was going on in the world. And they recognized that numbers, that mathematics would help them explain the world. And they wanted to classify things. This was an important thing. And they recognized that different kinds of numbers had different kinds of properties. And quickly they recognized that some numbers were created only through multiplication by multiplying 1 times that number. For example, there was no way to multiply two numbers that get 7 other than 1 and 7. Other numbers, like 12, can be made a number of ways. 1 times 12, 2 times 6, 3 times 4. What were these prime numbers? These numbers that could only be created by multiplying 1 by the number. There was no other possible factors. Well, Eratosthenes, a Greek who lived in Egypt in the 3rd century BC, developed a sieve that was used to identify prime numbers. A sieve is like a filter. And what he did, he recognized that 1 is neither prime nor composite. 1 is a creator number. All numbers are based on 1. So that was kind of put aside. It was a very special number. Then the number 2, of course, could only be created by multiplying 1 times 2. It was prime, and therefore any number divisible by 2, and you go through the number table and just cross out all the even numbers, could not be prime. Well, the next number that was not crossed out was 3. That was prime. But all numbers divisible by 3, 9 and 15, since 6 and 12 were already gone, were crossed out, and the next prime number was 5. And we can continue to do this. Eratosthenes continued to do this until he had reached the limit of his patience, I guess, and the numbers that had not been crossed out were the prime numbers. All other numbers were composite, and then 1 was this very special number. It was realized that 2 was the only even prime number. All other prime numbers are odd, and there's an infinite number of prime numbers, by the way. This led to an interesting situation that is quite, shall we say, sexist, because remember, the ancient times, males dominated. In many cases, women were just property. When a child was born in ancient Egypt, if it was a male child, you gave the child a name that had an odd number of letters. Of course, this was in Greek. If a female child was born, you wouldn't waste an odd number of lettered name. You'd give the female child an even number of letters in her name. And in fact, if you used an even number name for a boy, that was like today calling a boy Mary Sue. It would be very embarrassing. You wouldn't want to do that to your son. Even today, if you ask someone to pick a number between 1 and 10, most people will pick 3 or 7, odd prime numbers. Numbers had meanings for the Greeks and the Hebrews, because again, remember, the Greeks and Hebrews used letters in their alphabet. So numbers had meaning as words. For example, the Greek letter alpha, which looks like a fish, represented 1. And to the ancients, even before there were monotheistic religions, they viewed 1 as the creator number, therefore representing the creator God. And early Christianity adapted for many reasons, but one reason, the sign of the fish, which was also the alpha, the number 1. In Hebrew, the number 18 is a 2-letter word meaning life, chai. And many people today who are Jewish will make charitable donations or gifts in multiples of 18 in their currency. And the reason is they're donating for life, or giving the gift of life, if you will. The Greek spelling of Emperor Nero's name in Greek, and he had a very long name, wasn't Nero. If you took all those letters and added them up, you got 666. In the New Testament, this stands for the Antichrist, the sign of the beast. It is my understanding, I am certainly not a biblical scholar, it is my understanding that indeed when this part of the Bible was written, it was at a time when Nero was emperor, and of course the Christian writers didn't want to say in their Bible, this emperor, who's supposed to be a god, is really the antithesis of what we believe in, and therefore they used code. And the people who understood the code recognized they were really pointing out the negativism of Nero. But the Romans couldn't figure this out. I mean, they were prejudicial against Christians enough already. If they had evidence in their Bible of treason against the emperor, it would have been the end of that. So we see that we have numbers that have had meaning to the ancients, and even today. Again, ask somebody. Go out today and ask a bunch of people to pick a number from 1 to 10. Very few people will pick an even number, and most will pick 3 and 7. They will not pick 9. 9's odd, but it's not prime. So numbers have come into play. And in fact, in our next lecture, we will take a look at patterns in the counting numbers. So we'll see how the development of numbers that we've looked at in this lecture has come to play and to provide interesting patterns. And I look forward to seeing you in Lecture 2.